so I apologize for the delay, but now without any further delay, actually makes sense of Rutgers University.
Yeah, good morning. Pleasure to have you here, and I'll tell you something about how efficiently can easy dynamic programs be approximated. All right, so I think in this audience we all know what dynamic programming is, but just set the stage. So I have a problem P on input X, and what I do is construct a set of subproblems, which includes the problem itself. And then we're going to have a directed acyclic graph on the set of subproblems. And here's what we want, the initial subproblems. So the subproblems that don't have any, that are sinks, sorry, that are sources in the graph, that don't have any edges in, those are trivially solved. And every non-source subproblem, so every node in this graph, which is not a source, is easily solvable given the solutions to all of its integers. So that's kind of an abstract version of what dynamic programming is. And I'm going to focus on an easy class of dynamic programming, where the subproblem graph is a two-dimensional grid. So it looks something like this. The full problem will be the upper right-hand corner, and the trivial problem will be the lower left-hand corner. And sometimes the graph will have diagonals as well. Okay, so there's one of our subproblems. Again, we're being abstract. So each subproblem is indexed by just an ordered pair ij. And the setup is that Vij can easily be constructed, or is an easy function of, well, in the case when we don't have diagonals, then of the problem just to its left and just below it, or possibly with the one just diagonal. Okay, and the running time of this thing is order n squared, because you just march through the graph. There are n squared vertices, and processing each vertex. Well, I'm assuming that's constant time. Maybe it's logarithmic time. So, but we're not going to worry too much about log factors or small factors. Oh, I should also say. So I haven't said anything hard yet, but please feel free to ask questions, interrupt, break my rhythm if you want. Please do that. It's very easy, especially with a slide talk, to just march along with people drifting off. So here's an important subclass among these two-dimensional dynamic programs. So the problem instance, whatever it is, induces a cost function on the arcs. So each arc of the graph has a weight or a cost. And the cost of subproblem ij is just the, I think we're...
But leave it unlocked.
Yes, I'll leave it open.
The cost of the subproblem ij is just the minimum cost of the path from 0, 0 to ij. Okay, and it's easy to see that that cost, if you have that cost function, then that cost function is an easy so it's easy to see that that main cost is just equal to, you have to pass through one of the three nodes prior to this node. So if you've solved the subproblems just below it, then it's easy to calculate the main cost. So let's look at some examples. A very common thing is if you have some distance function between the two strains. So you have two strains, and say, I look at a string, and I look at the elementary operations. A character deletion costs 1, an insertion costs 1, a substitution costs 1. And the so-called Levenstein distance, or edit distance, between the two strings is the minimum number of elementary operations to change x to y. It is an easy exercise, which you may have done, but you could do it right now as you sit, that this is a symmetric function, that the number of changes, minimum number of changes to change x to y is the same as the number of changes to change y to x. And in fact, another way to think about it is that, and its equivalent is you don't have insertions, but you want to take x and y, and you can do substitutions on either x or y, and you can do deletions on either x or y, and you want to make them the same. And you ask, what's the minimum number of operations of just deletion and substitution operations to make the two strings the same. If you don't allow substitutions, then you get what's sometimes called insertion-deletion distance. And that's equal to the minimum number of deletions on either x or y to make the two strings. Okay, so if I have a distance function on strings, whatever it is, then we'll think of the subproblems as prefixes. You have a prefix of the first string going from symbol 1 to symbol I, and a prefix of the second string going from 1 to j, and you ask what's the distance between those two prefixes. So that gives you your n-squared subproblems. So we'll write that prefix as x less than or equal to I, or y less than or equal to j. Okay. Now, here's another example. This is not a string problem. This is a problem on a single string. So now you have a string x of numbers. And the distance to monotonicity is the minimum number of deletions to make x monotone. You want to make x an increasing sequence. So if you take the longest increasing subsequence, then this distance to monotonicity is just the length of the whole string minus the length of the longest increasing subsequence. So in this case, it's 3. Here's another example. This is another distance function, but quite different in edit distance. So to warm up, we have a string x of numbers, and what we call a traversal of the string is a sequence of steps where in every step you either stay on the same number or you move to the right one step. Okay, so that's a traversal of x. A traversal, you either move to the right or to the left. And a monotone traversal means you're always moving to the right. Okay. So if you look at this, the first one, I actually take steps backwards. The second one, I always just go. Okay, and for x and y, at equal length traversals, if I have a traversal of x and a traversal of y, then the sum cost of these traversals is, so you're trying to line up the traversals so they're as similar as possible, and you measure the distance between them. So in your traversal of q and your traversal of p, you take the absolute value of the difference between the two numbers, and you add that up. And in the max cost, you take not the sum of those differences, but the largest difference. And what's called Frechet distance is to minimize the max cost over pairs of traversals. And dynamic time warp distance is minimize the sum cost over pairs of only monotone traversals. Okay, So these are, distance measures that have been proposed in the literature and that people are interested in studying. All of them are computable by the dynamic programming paradigm by looking again at, calculating this thing for pairs of substrings.
You want to say anything why this last discipline has such a fancy name? It sounds like a very...
Why is it called dynamic time warp distance? Well, the time warp means, if you imagine that you're moving, that as you move from left to right, you're moving through time, right? But you're warping time, so some symbols you're staying longer, and you can control that. Okay, but you're trying to line up these two systems, and you can warp time in different ways for the two things. I didn't make up the name.
So is it clear that the Frechet distance is actually like solvable by dynamic programming? Because it kind of be allowed to go back actually.
Yeah, I can't answer that question off the top of my head right now. I'm pretty sure it is. Okay. So all the parameters above, well, maybe I might be lying about Frechet distance, but I'm pretty sure it's also some quadratic time. And the question, a natural question that has been studied for a long time on these problems is, can it be quadratic? So for distance to monotonicity, there are two papers from the 1970s which show that you can actually beat quadratic time, except there's n log n. So again, the distance to monotonicity is on a single string. What I should have said is, so what's the easy dynamic program for distance to monotonicity? Okay. So in that case, what you want to keep track of is your subproblem is two things. You keep, let's just for simplicity, let's say that, yeah, okay. Let's actually look at the entire array and sort it so we know what all the numbers are. And, let's make the numbers 1 through n instead of, the actual entries 1 through n. And now think in distance to monotonicity, you're going to have two axes. One axis is your position in the string, and the other axis is the actual number that appears there. And there are n possible numbers, and there are n positions. And the subproblem, the natural subproblem for this thing is, what is the length of the longest increasing subsequence that in the first I positions, all of whose entries are less than or equal to j. So you throw away the entries that are larger than j, and you calculate that. And it's easy to see that you can calculate that then by a natural dynamic program. I mean, by the dynamic program structured as I said. But there's more clever ways of doing it. So there's an end. It's perhaps not surprising just intuitively, because this is a problem about a single string, while the other problems are about pairs of strings. So this problem seems somehow naturally simpler. And the question is, well, do any of these problems have truly subquadratic? When we talk about truly subquadratic, so there is literature in which people have taken the n squared algorithm and saved a log n factor, a log squared n factor, and that's nice work. But when we're talking about truly subquadratic, we mean actually lowering the exponent from 2 to something, 1.9. Anything, any constant strictly less than 2. Okay, so a short detour. How many people are familiar with the strong exponential time hypothesis? So I'll just remind you. It's a hypothesis which is stronger than the hypothesis that P is different than NP. So it's a hardness hypothesis about satisfiability, namely CNF satisfiability on n variables with no bound on the clause size, such as arbitrary clauses. Well, that problem is solvable in 2 to the n time maybe times a small polynomial. You just try all satisfying assignments, and each one takes you polynomial time to test. And the hypothesis says that you can't solve it any faster, so you cannot reduce the exponent from 2 to the n to 2 to the 0.99. So, I think, I'm not going to discuss this hypothesis very long. I think, there is general belief that it's true, but not strong belief that it's true. And there's certainly people like Ryan Williams who are very skeptical of it. But it's still interesting because it's a barrier. We don't know any algorithms for this problem better than this. Okay. And then once you have, if you believe this hypothesis, well, there's a notion of Seth hardness, and which will apply here. So it's a reduction. So what it says is you can take CNF sat, or the application, and let's say take edit distance, and we're going to encode your CNF sat problem as an edit distance problem. But the usual kind of NP completeness encodings, the encoding is polynomial size, polynomial in the original problem. But here, the encoding size will be exponential in the original problem. That'll be 2 to the n over 2. So you'll take your SAT problem on n variables and encode it by a pair of strings of length 2 to the n over 2, where computing the edit distance, if the edit distance is small enough, you have some threshold, then that means the thing is satisfiable, and if it's large, then it's not satisfiable. Now, there are such encodings for all these problems. So if Seth is true, well, if you could solve any of these problems in truly subquadratic time, so like n to the 1.99, then you could use that algorithm to solve satisfiability by doing the encoding in time strictly in 2 to the 1.99, or sorry, in 2 to the 0.99. And so then you would violate strong exponential time hypothesis. So again, it's not, you could say this is not, it's sort of evidence that it's unlikely we'll be able to solve these problems in quadratic time, or it's motivation to spend a lot of time trying to solve these in better than quadratic time, because if you do, you'll show that the strong exponential time hypothesis is false. Okay, well, so let's leave that as an open problem, whether these things are doable in better than some quadratic time exactly. But then say, well, if we can't, if we can't solve that problem, then what happens if we are willing to settle for an approximation? Okay. So can these problems be well approximated? Can they be well approximated in truly some way? So there are some results of the hardness of approximation. It's Seth hard to get subquadratic algorithms. If you wanted to approximate Frechet distance within a 1 plus small factor, then that's known to be Seth hard. And there's some weaker complexity evidence that deterministic approximation within a constant factor close to 1 for edit distance or insertion deletion distance is hard to achieve. That's not Seth hardness, but it's some complexity theoretic evidence. But that's for deterministic algorithms, so you can ask what about randomized algorithms. Now, a slight digression. When one talks about approximation algorithms for these kinds of problems, there's two notions of approximation that are natural to consider. One is multiplicative approximation, so you have a constant C and you want to approximate within a factor C. So if C is 2, you're willing to approximate this quantity within a factor 2. Then there's an additive approximation. So in that case, we have a normalization of the answer. So the answer, for example, in edit distance, the edit distance between two strings of length n is some number between 0 and n. So if we normalize by n the length of the string, we get a number between 0 and 1. And then we can ask to approximate that number to within some additive error. And so that would be an additive approximation. And intuitively, multiplicative approximations are stronger than additive. Well, namely, if you have a multiplicative C approximation, so let's say you had a 1.1 approximation, then you could use that to get an additive approximation, which is like a 0.1 additive approximation. But that only works if your multiplicative approximation has a factor close to 1. If the factor C is large, like bigger than 2, then the additive approximation that you get from this is bigger than 1, which is useless because it's easy to get a 1 additive approximation. You just answer 0, and that's always a 1 approximation. So a large constant multiplicative approximation is incomparable to a small constant additive approximation. They're two separate problems. Questions on this? Okay, and so the focus of the rest of this talk, after this introductory portion, will be discussion of 2 lines of algorithms. So one is a constant factor multiplicative algorithm, algorithms for edit distance running at subquadratic time. And so that result comes from a paper with Michal and Chakraborty, Das, and Goldenberg. There was closely related work with that was independently done that gave a quantum algorithm, subquadratic. But there's, you see the ideas in the 2 papers. There were similar ideas in the 2 papers. And then there's follow-up work of Michal and I, and Rakensiak and Rubinstein, where, well, we get from, in the original paper, our running time of our algorithm is something better than quadratic. It's n to the 12/7. As I'll mention, there was an improvement of that by Alex and Domi, who spoke yesterday, to n to the 3/2. And what we get is an n to the 1 plus epsilon for any epsilon algorithm, both Michal and I, Rakensiak and Rubinstein, with the catch that the algorithm only gives you that when the instances are instances that where the edit distance is relatively large. Now that's a little paradoxical because it's already known that if the edit distance is small, for instance, if the edit distance was less than square root n, there's a linear time algorithm to get the exact answer. So when the edit distance is small, we know good algorithms. But our approximation requires that the edit distance be close to linear in the length of the strings. If you're somewhere between square root n and linear, it seems like one ought to be able to carry over one of the 2 algorithms. Both of the algorithms that I mentioned, the last 2, they're independent. The algorithms build on the first paper, but in completely different ways, but they both have the same limitation. But they're both very tempting. They should carry over to eliminate the restriction. Okay, so that's the first problem, that's one of the problems on this stuff. And the other is the distance to monotonicity problem, which again is that problem on a single string. Just find the longest increasing. So it's to find how many elements you have to delete to make the thing an increasing sequence. And there you can get an additive approximation in polylog time. So just to emphasize, that means that your approximation algorithm doesn't even look at the entire input, right? It's just going to somehow sample the input and still make a good prediction as to how many elements you need to delete. Good, so let me move on. So I'm actually going to discuss these in reverse order of what I just said. So the first problem.
Mike.
Yeah.
The subpart, I think, do you like just get the number, or do you like know the operations you go from?
Yeah, you can extract.
Because the other one, clearly you should be able to extract if you're doing polygon. No, it's just a rough guess.
That's right. That's right.
The first one you can actually do it.
Okay. So let's, so that's the introduction is over. We're on to the first problem. So if you fell asleep during the introduction, you can pick up. Here's this part of the talk starts fresh. Okay, so we have the distance to monotonicity problem. There's the input is an array of real numbers. You eliminate some numbers to make the resulting array increasing. And you ask what's the fewest number of entries you have to remove to do this. Okay. So, well, we want to approximate, and we do know methods if you have some simple problems on vectors, like suppose you wanted to approximate the sum of a vector, of the entries of a vector. Well, we know a way of doing that works not all the time, but reasonably well, and as long as the numbers are reasonably well behaved, which is take a random sample, add them up, and then scale up the answer to the number of entries. Okay, and depending on how scattered the numbers are, that can be a very good approach. So you could try the same thing. Take a small random sample of locations, compute the distance to monotonicity exactly on this subarray, and then scale up the estimate. And this example shows that's not a good algorithm. Why? Well, what is this? This is the numbers, in order, except that every other number is flipped. 1 and 2 is flipped, 4 and 3 is flipped, 6 and 5 is. So the distance to monotonicity is n over 2, or when normalized, it's 1/2 the array is the distance to monotonicity. If you take a random sample, what are you going to see? Somebody, what are you going to see? What?
Half of each sequence?
Well, yeah, but what you will see is an increasing sequence. Because you will never, if you take a random sample that's less than square root n, you will never see 2 consecutive entries. They'll be scattered. And any scattered set of entries is completely increasing. So if you take a random sample, you'll think that the distance to monotonicity is 0. But the distance to monotonicity is 1/2, and you can make this algorithm much worse. So you can divide the sequence into blocks of length k, let's say blocks of length 10, and every block is decreasing, but the blocks are increasing. So once again, now the distance to monotonicity is almost everything. It's 0.9. But again, if you take a random sample, you're unlikely to see 2 entries in the same block, so you will see a purely increasing sequence. Okay. So the first notable work on this problem was some work independently by Alon, Chazelle, Commander Leo, and Parnas Ron. Whoops. There's a missing name. It's Parnas Ron and Ani Rubinstein. Missing. And so they got a factor 2 approximation to distance of monotonicity. which corresponds to like an additive n over 2. So as an additive algorithm, it's not very good, but it still uses some very interesting ideas, and well, it does get a multiplicative, a good multiplicative. Now, so what I want to discuss, I want to show what that algorithm is in this section of the talk. I'll show what the difficulty is in improving that algorithm. And then introduce the key idea for getting the multiplicative algorithm, the 2 down to 1 plus epsilon. So the point about it is if we can get the 2 down to 1 plus epsilon, then we can use that algorithm as an additive approximation.
So you seem to focus kind of like, you seem to prefer additive approximation. So additive actually means you actually add some term which is like n over 10. Right. So why is that actually better than?
No, so it's not that, okay, so, you know, I'm cheating a little bit here. So the problem is, the running, so for distance to monotonicity, let me just say there is this one problem. There is a problem which is, if I'm trying to get a polylog algorithm, there is the needle in the haystack problem, which means, you know, finding something which is really a single thing that's hard to find. So if I have an array, and the distance to monotonicity is 1. That just means there's one inversion. So the answer is 1, but if I don't examine the entire array, then I won't find you. If I only examine, let's say, half the array or a third of the array, I'm very unlikely to find it. And I will not be able to tell the difference between that and a completely sorted array. So I'll be completely in the dark between the answer 0 and 1. So I can't really get a multiplicative approximation. So multiplicative, so what happens is the running time when you want a multiplicative approximation, the running time, you get a term which is n divided by the distance to monotonicity. Okay, so you get that plus some polygon. So I want to ignore, so this, by focusing on additive, you get to ignore that problem. So here's a geometric view of this problem, which is kind of useful. So let's think of, well, x. Now I'm confusing things because before x was the name of the whole string. And unfortunately, I made the unfortunate choice. Now x is an index into the string. So make that switch. So x is either 1, 2, 3, or 4. And p of x is the point x, which is x comma f of x. So now I'm calling the array f. Okay. So, you know, you just plot the points. Okay. And now an increasing sequence is just a set of points going up to the right. It's geometric vector. And a violation is a pair of points which are not, well, so those are 2 points that are out of order. And the key thing that you have to realize, what you want to do is, when you are doing distance to monotonicity, you want to find the smallest number of points that cover all violations. What I mean is, for every violation, you have to remove one of those 2 points. So you want to think of, I want to pick a set of points in such a way that I hit every violation. Here's the general approach they take. So, first thing I'm going to have underlying this thing is I want an algorithm, which I'll call point classification. So point classification will take as input 1 point of this sequence. Let's say I give you the index, and that tells you the point. And it will either call that point good or bad. And it'll do some computation. So it's going to, if I want to decide whether this guy is good or bad, I'm going to look at some of the other entries in the array to decide whether this guy is good or bad, but then I'll make a decision. So I color the good points green and the bad points red, and there are two properties I want about. I want that the good indices form an increasing sequence, so the guys that I call good. And so the guys that I call bad are a possible choice of the guys that I delete. And what I want is that the number of bad guys should be close to the distance to monotonicity. So my algorithm for bad, sort of the best algorithm would be the one which figures out the distance to monotonicity and calls the guys bad precisely if they're the guys you want to delete. But that seems to require looking at the entire array. But what I want to do is somehow have a classification where I cheaply classify each point to satisfy these two properties. And if I can do that, then I can now, how would I use that? If I had such a good classification system, how could I use that to get a fast algorithm? Well, once I have a good classification algorithm, then you can choose a random sample. But you don't do what we did before, which was find the longest increasing sequence of the random sample. No, you don't do that. You run the classification algorithm on each point in your sample, figure out what's the fraction that are classified bad, and output the fraction of indices. Whoops, I should have said classified as good. It should be classified as bad. So that will be your estimate of the distance to monotonicity. Okay, and so since random sampling works, if you're just trying to tell what fraction of a population is good or bad, so you can do this with random sampling, but the key thing is, how do you get this classification? So what do we need from the classification? So we need two properties. We said that we wanted that the guys declared good should be an increasing sequence. So let's turn that out. So for badness to be a safe criterion is that if you have a violation, remember a violation is a pair of points out of order. So your badness has to have the property that it classifies one of those two points as bad. So we have to somehow guarantee that for every violation. And that will imply that good is an increasing sequence. And the other is the efficiency criterion for badness, which is that we don't want too many bad points. So we want that the number of bad points we declare bad should be at most, let's say, twice the distance. So I think the most mysterious part of this is how can you hope? So I pick a point, x, that's an entry of the array. And I want to decide whether to call it good or bad. And I can look at some other guys, a few other entries in the array, and somehow use that to declare whether this guy's good or bad. And somehow I want to be sure that globally that algorithm will declare, will meet this safeness criterion, that for every violation I will declare one of them bad. So here is this nice trick. So if I take a violation, so P of X and P of Z, they're out of order, and I look at all the points in between them, well, for every point in between them, notice that top point, the leftmost point, which is up high, is a violation with P of Z. And the one in the middle is a violation with both P of X and P of Z. And the one on the right is a violation with P of Z, but not with P of X. Okay. But it's easy to see that every point that lies in between them has to be in violation with either P of X or P of Z. That means that half the points in XZ are in violation with X, or at least half of them are in violation with Z. So that suggests the following approach to calling something bad. So I'm going to give you something with an inefficient algorithm, which is worse than looking at everything, but still it gives you a hint. So you say, okay, if I have, so what I want is, for any violation xz, at least half the points in xz form a violation with x or z. So a safe criterion for badness would be declare x bad if there is an interval with endpoint x. So if you have an interval with endpoint x, such that x has a violation with at least half the points in that interval. So let's see how that works. Here's x. So you're given x as input, and now you search through alternative points as the other endpoint, and you look at the interval there, and then you want to determine how many points are in violation with x, what fraction. And if more than, in this case, there are 7 points, and more than half of them are in violation with x, so you declare x to be bad in that case. But as I just described it, that's a very costly process, because you have to search over all the possible z's, which are every point with which x forms an interval. You check, and then you have to, then by checking for every z, you have to then check within the interval from x to z what fraction are in violation. That's already a quadratic algorithm. Okay. But now the nice thing about those operations is those operations can be approximated well by random sampling. Okay. So to decide if x is bad, we have to check each interval with x as endpoint. And then we have to, for each interval, we have to check all points within the interval. But we can do this approximately. So you take, if you take x, instead of searching for all intervals, you're going to take a logarithmic number of intervals with some factor like 1.01. 1.01 length, 1.01 squared, etc. And we just check all those intervals and see how it is. And then within each interval, you can check whether the violations just by, again, randomly sampling within the interval. So the overall cost of that will just be polylogarithmic to test any given x. Okay, so our testing for badness will actually only require polylogarithmic time. Now the question is, how good is the approximation? Okay, so we're going to declare every point bad. We want to declare a point bad if there is an interval where it belongs to a violation, and where at least half of them are in violation. And if you were to do that, which we're not doing that because we're doing an approximation of that, but we actually did that, then there's a lemma, which is not too hard to prove, which is the number of points which have this property that there is an interval where they're in violation with half the points in the interval is at most twice the distance. Now, when you do the approximations, meaning you do the random sampling, well, you have to lower the criterion. You have to, in order to be safe, instead of saying that I'm going to eliminate x or call it bad, if at least half the elements, I'll have to do it if at least 0.49 of the elements. So I have to lower the criterion a little bit for badness. That will increase the factor from 2, from a factor of 2 to a factor of some 2 plus delta. Okay, so putting it together, you sample a set of points, determine the fraction that are declared bad. So you're going to sample a set of points, figure out which ones are declared bad, and then just estimate that fraction, and what you end up with is the ADM is at least DM, but it's at most 2DM, and the approximate, that's all approximate. It's so small. Okay, so that's their algorithm. It gets this factor of 2 up to this additive error. And what we were setting out to do was to see, can we replace the 2 by 1 plus epsilon? So you could look and say, well, can I improve this algorithm? What can I do with this algorithm? And so let's look at the high-level structure. So first of all, we have a classification algorithm into good and bad points. And we want good to be good. And bad, the size of bad overestimates the distance to monotonicity. Right now, it might overestimate by a factor of 2. We'd like to get it to overestimate only by a factor of 1.1 or something like this. Now, how is the classification done? Well, there was some stuff we did, but at a high level, what did you do? We took a random sample of indices where the distribution was not purely random, but we had a random sample of indices where the distribution depended on x, and then we examined the points in the random sample and used those to decide whether x is good or bad. So what is that sample in the case of their algorithm? So I want to say, so here's the structure of the sample that they look at. So let's go through. What we said was we took logarithmically many intervals of increasing size. And for each one of those intervals, we took a small random sample. Now, if you think about that, what that means that points nearby x, so my overall random sample is the union of all the random samples I took for every interval. And what that means is that sampling near x, I'm going to be sampling fairly densely. But as I get farther away from x, I'm going to be sampling much more sparsely. So kind of the shape of that sample, the density of the sample decreases exponentially with the distance from x. Something like this. And I will say, if you think about it, it makes sense. I mean, kind of that's the way the algorithm works, and that's the way. But, you know, what else could you do? You're only allowed to make samples of polylogarithmically many samples. If you make them uniformly, it makes sense that the ones near x are sort of more important to deciding about x than the ones far away. Okay, so now we can ask the question, suppose we had a sample of this form. Is there a better way to classify x using the neighborhood samples? Better in the sense that we can classify x in a way that the points we declare bad still satisfy the criterion that when I remove them, what I have is increasing. But also, I want that the points I declare bad, right now it's twice the distance to monotonicity. I'd like to get it down to some small, just bare, like 1.1 or 1.0. And can we do this? And so now the following example, which takes a little bit of studying, but not too much. So these are this is the graphic representation of two sequences. So the first sequence increases steadily for a while. Okay, and then there were two sequences, increasing sequences of length, each of length k, that are interleaved, jumping back and forth. And then you have a sequence of length 2k. Okay, and in the other one, it looks sort of similar. The first two sections are the same. But in the last portion, instead of having an increasing sequence of length 2k, it's split up into this kind of thing where it's a bunch of short decreasing sequences, each one is increasing. So those are two things. If you look at these two sequences, you compute the distance to monotonicity. In one case, it's 2k, because the guys you will delete are just the guys above the dotted line. That will give you the best. And in the other case, the distance to monotonicity is 3k, and the guys you delete should be the guys below the dotted line. Okay. Now notice that look at this first interval of length k. Okay. Well, in the first case, you want to declare everybody in that first interval of length k bad. Because if you declare anybody in that interval good, then you are going to be forced to declare everybody below the dotted line bad. So you absolutely need to declare, in the first example, you need to declare everybody in that first interval of length k, you have to declare them bad. And in the second interval, well, you want to declare those guys good. If you declare them bad, then you're going to, just a minute. If you declare them bad, then you are going to end up increasing the distance to monotonicity. Then whatever numbers you declare bad, you're going to end up paying that as a value. Okay. So now, but now you want the classification algorithm to behave differently in one algorithm than the other on those points. But how is it going to do that? So notice, the only difference between these two sequences is in this portion in the last 2k. And in that portion, your neighborhood sample is sampling very sparsely, because that's a portion that's far away from this point. So you're sampling sparsely on that section, and you can't tell the difference. If you take a sparse sample of that 2k, because you're just going to see an increasing sequence in both cases, if you take a sparse sample on the left and the right. Okay, so it must be bad in the first, it must be bad in the second, or else you're going to screw up good in the second. So to beat this approximation factor, the good-bad designation for P must depend on small-scale properties of the sequence far away from P. And so neighborhood sampling is insufficient. So I'll say, when we came up with this example, our reaction was, okay, what we're trying to do is impossible. It seemed like, how are you going to take advantage of, how are you going to pay attention to, how are you going to make some classification? Well, of course, your algorithm doesn't have to have this paradigm. But, you know, so then we switched to trying to prove a lower bound. And, you know, algorithms are sometimes proofs that lower bounds don't exist, and that's what exists. That's what happened. Okay. So now let me just tell you what the basic idea of the algorithm is. Okay, so we're going to view this dynamic program. So there is this dynamic program, and you can view a dynamic, one way of visualizing a dynamic program, or this dynamic program, is in a divide and conquer. So what I'm going to try to do is, I'm trying to find the distance of monotonicity, which is the same as finding the longest increasing path. It's the complement of that problem. So I can think of the problem in this way. So what's going to happen is, when I get through the first half of the sequence, in the path that I choose, in the best path, there will be a certain height that I will have reached. Let me call that height y. And let's imagine that I guess what y is. So I guess what's the height that I reach when I get through. So if I were able to guess y, then I would break up the problem into find the longest increasing subsequence in box 1 and the one in box 2. So the distance monotonicity is the minimum over y, so you choose the height, of the distance of monotonicity in box 1 plus the distance of monotonicity in box 2. And we'll call this pair n over 2y as the splitter. It divides you into two problems. And for approximation, we only need to check, we don't have to check all possible y's. Turns out it suffices to check polynomial y's. So if you take, let's say, evenly spaced y's, polynomial, then you do this kind of calculation. Now we want to use this to try to do the following. So if I give you so here's the thing we're trying to do. Suppose I had an algorithm, which is an additive tau prime approximation. So, you know, whatever tau prime is. And I want to use it to get a better approximation. So I want to use a weak approximation algorithm to get a better approximation. Well, this is, so we're trying to boost the approximation. Okay, so suppose we magically find the best splitter. We have n1 points here and n2 points here. And we have the points that are outside the blue boxes. Now those are points which you're going to pay for. Those are part of your distance to monotonicity, this W. So we run an additive delta prime approximation in box 1. That's the worst approximation, the bad approximation, or the not as good. We run the delta prime approximation in box 2. So the distance to monotonicity overall is the distance to monotonicity in box 1 plus the one in box 2 plus the white points, the W points. And your approximation is the approximation in box 1 plus the approximation in box 2 plus the approximate number of W. And you're going to approximate W by a random sample. Okay, so W approx will be pretty good approximation. And we're promised that ADM1 minus DM1 is the most delta prime, and DM2 minus DM2. Oops, that should be DM2 minus ADM2 is the most delta prime of 2. And what we want is ADM minus DM is less than delta n, where delta is some constant strictly less than delta prime. And it kind of looks like, well, when you add these inequalities, you're going to get this difference with delta prime, right? Why should you hope that delta is going to improve? But what we can say is, well, ADM minus DM is delta prime n1 plus n2 plus W minus W approx. And the point is that n, the number of points, is not n1 plus n2. It's n1 plus n2 plus the number of white points. So if the number of white points is reasonably large, not like 0.01 n, well then you'll get n1 plus n2 is going to be less than 1 minus mu n. And so W minus W approx is now negligible. So ADM minus DM is less than delta prime times 1 minus mu. Okay, and that delta prime, therefore we call that delta. That's actually strictly less than delta prime. But that's under this assumption that W is at least. So we have that assumption. What if the assumption fails? Well, the nice thing is that if it fails, what that means is there are very few points in the white boxes. And that's actually a proof that this particular choice of Y is very close to being the optimal choice. In other words, that if you make the choice that that is the way this thing splits, then it turns out that that can add an error of at most this amount W. So the fantasy algorithm is to get a delta approximation, search for a splitter that violates the assumption. So try to find a splitter where the number of white points is really small. And if you do it, then you can be guaranteed that that's nearly optimal. And since it's nearly optimal, then we can just run a delta approximation on two smaller subproblems. Otherwise, boosting, then we don't know which is the optimal splitter, but we take polylog n ones, and on each one we're going to cursively solve the subproblems with the worth additive approximation. Okay, so that's the basic idea of the algorithm. The real algorithm has a bunch of technicalities. You have to search for a splitter that violates the assumption. That's okay. But the splitter that violates the assumption is close enough to optimal. That doesn't quite work. You have to redefine, careful redefinition of what you mean by a good enough splitter, which that's technical, I won't get into. Also, the divide and conquer we divided the problem into 2 subproblems. Turns out, to get the computations to work, you have to divide it into polylog n many subproblems. So the algorithm is a bit of a mess, but eventually works out. Okay, so that's all I was saying about. Let's see what we got. So, what? 20 minutes. Okay, so let me say something about edit distance. So we're moving on. Again, this is an opportunity if you've tuned out. You can tune back in because we're starting a third talk. Okay, so we're looking at edit distance. I'll remind you what it is. You have elementary operations. You pay 1 for a deletion, insertion, or substitution on a string. And the edit distance is the minimum number of elementary operations to change x to y. And for exact algorithms, there are a bunch of algorithms known, the order n squared dynamic program. I mentioned if the distance is k, if you know that these strings are relatively close, or even if you don't know, there are algorithms whose running time is n times the actual distance. Okay? So that means that this is what I'm saying, is that you can actually reduce, and there's even a better algorithm which runs in time order n plus k squared. So if the actual distance is less than root k, then you have a linear time algorithm for the exact problem. So this makes precise what I said about empirically we know, in terms of what we know about the algorithm, the problem definitely seems to get easier as the distance gets smaller. The best unrestricted algorithm for the exact problem is this one, which saves essentially a log squared n factor. Now for approximation algorithms, there's a sequence of work. I won't go through all of it, but you'll see that the approximation factor started out fairly bad, square root n. So it's multiplicative approximation. It was n to a power, but all these algorithms are running in close to linear time. Actually, one of them is even sublinear, n to the 1/3 time. But then there's the algorithm which gives a polylog n approximation factor running in close to linear time. That was Anthony Kraft. Okay, actually I didn't move this slide, but this is just this. Let me solve this. So the main result here is there is a randomized algorithm, edit distance upper bound, that on input strings x, y of length of next n runs in time about 8 to the 12/7. Outputs an upper bound on the edit distance that with high probability is at most some constant times the true edit distance. So it overestimates the edit distance by some fixed constant. In our paper, the constant is, I think maybe it's a little lower now, but it's not so good. But one, if you cared enough, you can easily read the paper, and we give up factors of 2 as though they were candy. So there are at least 5 factors of 2 that could be saved immediately. But the point is that it's a constant, and what that constant should be, well, maybe it should be like 3 or 5 if one does it carefully. So then there was subsequent work of Andoni, applies and improves on the basic method to get runtime order into 3 halves. And then this recent work I mentioned that you get a constant factor approximation in n to the 1 plus epsilon time. But it requires, it's only on inputs whose edit distance is nearly linear. Which should be the hard case, as I said. But, okay, so back here, that's the main result again. And then there's a key lemma, which has a bunch of parameters. Yes?
Do you need, do you also, would you need more than that? Because I guess if the distance is smaller than that, you said you have m times k algorithm also. So that would take care of any, that would already be subquadratic.
It would be subquadratic, but the result
Oh,
that
no,
I mentioned,
right.
n to the 1 plus epsilon.
Oh, right, yes, right, thanks.
Okay. So here I'm going to say this is a common thing if you've ever done approximation algorithms. Approximation algorithm is you get an instance and you want to just approximate the answer. There is a problem called the gap problem where you just have two values. You have a lower bound and an upper bound that are, let's say, within a constant factor of each other. And you want to just tell the difference. So you want to identify those guys that are definitely below the lower bound and the guys that are above the upper bound. And for guys in between, you don't care. You can answer either way. So that's what's called the gap problem. And so what we end up doing is solving a gap problem. And that's what we'll focus on. So imagine you have a number theta n, and you want to tell the difference. Is the edit distance less than theta n or more than 840 theta? Okay, we saw this picture before. The edit distance is the shortest path problem. So the horizontal, so if you think of a horizontal edge, you have the two strings, and a horizontal edge corresponds to delete the symbol in the horizontal string, which is x. And going on a vertical edge is to think of it as the instruction, delete the symbol that you're looking at in the y string. And a diagonal edge means make the substitution of the symbol in the x string by the y string. So if you do that, then you just see, and if you think about it for a minute, you'll see that. Now, the cost of an edge of the horizontal and vertical edges is 1. The cost of a diagonal edge, well, it's 1 unless those two symbols happen to be the same, in which case you don't have to do the substitution. The substitution is free if the symbols are the same. So the only thing that this picture depends on the input is how the diagonal edges are labeled. They're either labeled 0 or 1. Okay, and then the dynamic program has the same structure. And the subproblems that we'll talk about a subproblem, which is defined by a substring of the bottom. It might not be a prefix, just an arbitrary substring, the bottom and the top. And you ask, what's the edit distance between those two substrings? Okay. And that's the same as the minimum cost path from the lower left to the upper right. That box. Now, if I have a subproblem, I will call a certified box is a subproblem, which is this I cross j, together with a number where I know for sure that the cost of I cross j is at most c. So I'll call that a certified box. And we're going to have the following paradigm for approximation. So it's a two-phased algorithm. In the discovery phase, we discover a set of certified boxes. So we're going to do something to certify a bunch of boxes. And then the inference phase, we're going to take the certified boxes and combine them to infer an upper bound on the edges. So let's talk about the inference phase, because that's relatively straightforward. So for every certified box that I discovered, I put in a shortcut edge in my graph whose cost is the value c. So I just build the shortcut graph associated with all the certified boxes I discovered in phase 1, and then compute the cost of the shortest path. Now, shortest path algorithms run in time which is proportional to the number of edges. this graph has n squared edges because it has all these. It has the grid. It has the shortcuts plus the grid. But there's a customized version of the shortest path algorithm where you only pay order or O tilde of the number of shortcuts. And that's actually a nice, so instead of paying for all the edges, which is quadratic, it's a nice algorithm, a nice exercise for an intro algorithms class to put that together. Okay, let me also mention that there are these things called, an induced box is the following. So I have I across JC. Now, if t is an integer, let me take the interval j and shrink it by raising the lower endpoint by t, and the upper endpoint decreases by t. So I'm shrinking it by 2t in both directions. So if I have a certified box, then the box I cross j minus t, it's not hard to see that you get an upper bound. If you shrink, if you know the distance between I and j and you shrink j, then the distance between these guys can only increase by the amount that you shrunk j. So whenever we find a new certified box, I cross JC, we'll add a bunch of induced boxes where t is going to be powers of some, let's say powers of 2. Okay, so that's the, so we think of, we're going to do in the first phase, the discovery phase, we're going to try to find certified boxes. We find the certified boxes, we take each certified box, we add these log-in induced boxes, which we can get. We build the graph, and then we find the shortest path. So the main work, and the main focus of the last 5 minutes, will be, how do we discover? The discovery phase, what's needed. So we have an unknown shortest path. And it suffices that the set of certified boxes includes an exact cover of the shortest path. So if I happen to find, now I don't know where the shortest path is, but if I happen to be lucky and I find boxes which cover the shortest path in this way, then I compute the, the cost of each of them. And if each of these certified boxes is I have a pretty good approximation of the edit distance, then when I piece them together, if I put in the shortcut edges, those shortcut edges will form a path. And if everyone is certified by its true cost, the shortcut edges together, that path will have cost exactly the edit distance. Now, if it turns out that if the boxes that you find aren't an exact cover, but they're an approximate cover, look at something like this. And most boxes are certified by a reasonably good upper bound. And all that has to be being precise. Then that's good enough. If the discovery phase finds a set of boxes like this, then that will be good enough for the second phase to actually get a good estimate. So let's call that an adequate cover of the path by boxes. So how do we ensure an adequate cover? So it suffices to look for square boxes, so we'll restrict attention to square boxes. We're going to divide this whole thing into vertical strips of width W1 and certify, and we're going to try to certify sufficiently many square boxes in each strip. So in each strip, we can just look at, shift the vertical interval and look at every one of these boxes. And that's sort of an exhaustive approach. And if you count up the number of boxes we have to look at, well, the number of boxes you get is like n over w1 squared. And each one you have to solve an edit distance problem, which costs w1 squared. And the overall cost is more than n squared. So that's not some quadratic. So that's not so good. And we're going to try to beat exhaustive discovery in 2 ways. So we're going to reduce the cost. Right now we are paying w1 squared to certify intervals. So we want to reduce the cost per box of certification. And the other thing is we want to reduce the total number of boxes certified. So we want to try to make progress, and we're going to do a combination of these. Okay, so idea 1, we're going to use the triangle inequality to achieve an economy of scale in certified boxes. We'll see how that works. The idea 2 is we're going to use boxes of small width that have a small cost to pinpoint large boxes that are important. So right now so I'm going to have about a minute to show you how each of these ideas works. So certifying many boxes cheaper. So pick an horizontal interval I. Find all intervals that are horizontal. Oh, sorry. Find all vertical intervals that are close to I. Let's say you find them. Find all horizontal intervals that are close to I. So that means the substrings have small edit distance. Okay. Now, you had to compare I to all these strings to find all these guys. But once you've done that, what we know is that if you take any one of the red intervals and any one of the blue intervals, then by triangle inequality, the distance between them is the most 2k. So for all those boxes, you were able to certify them to be at most 2k. Okay, so that was the first idea. And you notice that idea is useful provided that this particular interval was close to a lot of horizontal and vertical intervals. If it was only close to a small number, then that will not give you much economy of scale. Okay, so the next idea is pinpointing a small set of significant boxes. So I have an interval I, and I want to determine which boxes, which vertical intervals might be important for I, which means which ones are going to be, which ones are possibly close to I, because that's what I want. So here's what I do. I pick a small random interval, I prime inside of I, find all vertical intervals close to I prime. That's those 2 blue ones. Look at the associated boxes. And if there aren't very many such boxes, then what we'll do is take each of those boxes and diagonally extend them to a box on I. Do that same thing here. And then we will call those significant boxes, ones that we ought to check. So we have a dichotomy. For a horizontal interval I prime, if there are many intervals close to I prime in edit distance, then we can, that's both horizontally and vertically, then we can use economy of scale to certify many boxes cheaper. If there are few intervals close to I prime, and there's a lie on this slide, but we're at the end of the talk and there are plenty of lies. But the basic idea, if there are few intervals close to I prime in a distance, then take the induced boxes, diagonally extend them to the superinterval I prime to get a small set of interesting boxes for I. Okay. And those will be our 2 sources of certified boxes. We put those together, and after a certain amount of analysis, one sees you get what you're looking for, which is that you're able to cover, even though you don't know where the shortest path is, you've found enough boxes that you're likely to cover the shortest path. So, ignore that. That first line is supposed to be accurate. So, the first thing is for edit distance. As far as we know, it could be the case that for any epsilon, I can get a 1 plus epsilon factor approximation that runs is better than n to the 1 plus epsilon. Okay, as far as we know that. So you could get what would be called a quasi-linear approximation scheme, or even n times polylog. At the moment, our algorithm, the constant factor approximations, as you reduce the time n to the 1 plus epsilon, the constant factor approximation grows with epsilon. It's not clear that that's absolutely necessary. It seems to be necessary in the algorithms we have. You can look at other distance measures. There's nothing dynamic time work distance. You can look more generally at dynamic programming problems on grids. We were looking at ones that are defined on substrings, but there's this general class of dynamic programs. And can one say, in general, those are all quadratically solvable? Can you approximate them, or some subclass of them? That's it. So, that's all.
Thank you. Questions? No questions. So let's thank the speaker again, and let's thank Ormin in 11:20.